anniversary conference for the International Tesla Society. We have for you three elements in our presentation this morning. The first, a series of slides. Secondly, a videotape preview of a new magnifying Tesla coil system, which will be exhibited at Penrose Stadium on Saturday night, July 23rd. And that coil is patterned on a 1-to-1 scale, nearly so, as compared to what Tesla did here in Colorado Springs in 1899. Magnifying Tesla coils, what does that mean? It means a three-element coil system, a primary, a secondary, such as you see here in front of us, and then some kind of a electrical connection to a third element coil, which Tesla referred to as an extra coil or a tertiary coil. That is the magnifying element. The electrical and physical parameters of the primary and secondary of a magnifier system are necessarily different when used for a magnifying system as compared to a standard two-coil primary and secondary only system. The form factor on this secondary here is approximately 1.5 to 1. That is, the height of the coil is 1.5 times the diameter of it. The inductance of this coil is relatively low in terms of standard two-coil construction techniques. So the idea with a magnifying system is that at the output of the first secondary, you want to have only a moderate voltage rise and a very large amount of current. That is what we call the injection voltage to the input of the extra coil. The inductance relationship between an extra coil and a secondary is very significant. We want to demonstrate that by replacing this extra coil with another extra coil of vastly different construction so that you'll see what the difference is in the output without changing primary tuning. All right, to begin with, I want to go over some slides which I have, which are a good refresher element to review some of the most significant points of all Tesla coil construction, which is also true for magnifiers. On the screen, we have a slide which I normally show at the beginning of all of my presentations. How many of you recognize what this slide represents? Anybody know? One person here, okay. This is the Griffith Park Observatory and Planetarium in Los Angeles, California. This is the coil that I first saw as a child in 1956 that got me started on the path of interest in Tesla and Tesla coils. Having seen this coil, I decided I had to build one. I thought it was the neatest thing I'd ever seen. So I got some baling wire and some steel banding tape from the trash can, and I made my own coil. I used a little erector set motor with a little small brass circular disc that you typically get in erector sets, and the kind of wire brush elements that you can find laying around in the street left behind by the street sweeper was my commutator brush. I didn't know that you actually had to have a spark gap in the primary or a capacitor or anything else. So what I had done was I had taken a couple of these whiskers of these flat steel blades, and here was this little erector set motor running on 110 volts, and this little brass disc with flathead screws on it. I think there were 8. So the gap wheel diameter was maybe 1.5 inches, and whiskers just barely contacted the surface of the flathead screws. And I hooked that in series with my steel banding tape primary made in the form of an Archimedean spiral. And the wire for the secondary, as I recall, I had robbed my father's workshop of a roll of 500 feet of the kind of wire that you use for lamp sockets. That is, it was an asbestos-covered wire, probably about 14 gauge. And I made a wooden coil form out of 1x1s and plywood so that I had a conical secondary. I tried to emulate this coil's design. I then proceeded to plug it into a 110 volt wall socket. And I promptly tripped the 20 amp breaker. So then I reasoned, well, I need some kind of current limiting device, so I got a 1,000 watt light bulb and put that in series with the spark gap, if you will, in the primary coil. Well, now the light bulb glowed brightly, but it flickered because of this mechanical commutator, which I thought was a rotary spark gap. And I was very disappointed when I took a ground wire up to a little tiny doorknob ball that I had found, which was my discharge electrode. I actually did get a spark. It was maybe a 32nd, maybe a 64th of an inch, and that's all it was. That almost stopped me dead in my tracks as far as Tesla coil construction is concerned, but of course, it didn't turn out that way. Anyway, so much for the first slide. I imagine all of us have stories to tell when it comes to our first coil experience. Tesla, of course, started out with coils similar to this, which were hybrid modifications of standard induction coils. In this particular instance here, and I'm pointing with this red laser dot to show that this was a mechanical interrupter replacing the standard vibrator circuit typical of an induction coil. And the primary secondary as a coaxially wound solenoid in the background was actually an air core system. So it was running on DC, but yet still producing high frequency alternating currents across the discharge gap. This picture here, if we can adjust the focus in the back there, I don't know if we have autofocus adjustment for this projector or not. I must apologize that this slide is rather severely out of focus. You see a 20-inch toroid here and long corona streamers coming off. There, that's perfect right there. These streamers are nearly 45 inches long. The secondary coil that you can't really see in the center here is only 20 inches tall and 5 inches in diameter. This is what I call a Model 5 coil, very successful coil system. Many of these placed in a number of museums throughout the United States. We just went out of focus again. So there we go. We'll go on to the next slide. Here is that same coil in operation, and you can see a breakdown between the primary and the secondary. And this is what is known in the early literature as a d'Arsonval breakdown, meaning that it's moderately low voltage and very high current, very destructive to the windings of both the primary and the secondary. And you'll notice that the discharge is again playing all over the surface of the toroid. That discharge, by the way, is indicative of improper coil tuning or overcoupling or simply overdriving the coil system. It could be any one of those three anomalies. Here we have a view of the base of a Tesla coil that was built by a friend of mine by the name of Richard Arant, who also began his Tesla coil career, if you will, by being exposed to, guess what, the Griffith Park Observatory coil. Only in his case, he saw it in 1951. So by 1954, he had built this system. He built this coil, two capacitors down below, the rotary spark gap, and a series stationary gap from an old electrotherapeutic diathermy machine. The primary, again, a flat Archimedean spiral. This is aluminum sheet, and it's actually 4 layers together, forming 6 turns. The secondary coil form was a sonotube, or cardboard tube, and what you see here is not actually the wire or the insulation on the wire, but rather hemp rope, because if you look at any of the Hugo Gernsback publications, Practical Electrics, Electrical Experimenter, one of the common techniques that was a standard signature of coil design and construction in those days was to place a non-shorting metal band around the bottom and also near the top to prevent the burning of the wire insulation. And you can see here that in addition to the metal band at the top, there's also an aluminum top disc, has a sharp edge. So guess what? You have a lot of leakage, a lot of corona leaking off here. This is that coil, the Arant coil as I call it. I inherited that coil after Dick Arant passed away. and has since been donated as permanent exhibit to the International Tesla Society Museum as of just over a year ago. You'll notice also that there's a sharp issuance of corona discharge here. That's from a metal ball and a double-pointed corona rod that is, again, patterned after what the Griffith Park Observatory had done. One of the things that's interesting about this, if you'll notice, these discharges issuing out from this top plate here start to form an arc. They don't come straight out. They actually follow almost a hemispherical arc. And I would submit to you that what you're seeing there is ionized corona streamers that are following electromagnetic lines of force about this solenoid or about this secondary coil. The light here at the bottom, of course, is from the rotary spark gap. If we take a closer look at the top of this coil, you can see here again the amount of corona discharge leaking off that aluminum top plate, which was placed there for no other reason other than to save the top of the secondary winding from burning up. Here, of course, too, in this case, I believe it was about an 8-inch copper ball and the 2 corona points. So, in terms of modern Tesla coil construction, you might say, well, this looks very pretty. However, it's not that effective or that efficient. It would be far better if we could take all of that energy and store it in a terminal capacitance or discharge electrode of some form or shape and have the discharge build up to a much higher voltage level before it breaks down. Here is a time exposure of the same coil operating. Again, notice the corona leakage coming off the top plate here. And you'll also notice the large power arcs going over to a grounded rod here to the right. This gap distance here approximately 4.5 feet, and the time exposure approximately 3 seconds, and the input power approximately 2 kilowatts. Well, what I have done here, and you'll see in the next slide, I've replaced that copper ball with those double corona points with an aluminum toroid, very similar to what we have here today, and put a small corona point sticking out just about 2 inches from one surface of that. And now these discharges here are quite a bit longer because of several things. Number one, we have more terminal capacitance or larger loading capacitance for the secondary to look into. Secondly, we have more stored energy before breakdown because of the physical geometry of that discharge electrode. Looking here at this shot, now notice that from that single corona point, we have all of this tremendous corona activity. We have discharges of very high current as witnessed by the signature of the blue-white color of these power arcs as opposed to the lavender-purple color of the free air corona streamers. This is a 6-foot-tall aluminum ladder that was grounded. And you'll notice the striations of the discharge showing the individual pulses of the 60-cycle charging current. And you'll also notice, if you look closely, that same metal disc is still here about the top of the coil, and just a very, very faint corona glow, hardly visible at all. And still, it has that characteristic bending down. It's not just a straight-out axial glow sheet. It's actually bent down on a slight angle. That's due to 2 reasons. Number one, the electromagnetic lines of force set up around the solenoid or secondary, as I previously had mentioned, but also because of like sign repulsion, because the E field or voltage field gradient set up around this toroid is of the same sign as the corona ionization here, and since that is true, you would expect that field to be deflected slightly. Here again, running at 2 kilowatts, the same time exposure as in a slide previously seen. And now in this case, I would like to say that after a discussion with Richard Hull from last night, it's amazing how experimenters come together and pretty much do similar things. That is a single 1/4-20 nut, a standard machine nut that was taped on to the side of this toroid. And now, here again, the gap length almost 6.5 feet to this same grounded ball here. And again, notice the intensity of the power arcs in that discharge. These elements are all important to study, not only for magnifier design, but for any Tesla coil. Here, on the right, we have a separate secondary. It's a fiberglass form, 9 inches in diameter, about 6.5 feet tall, 20 gauge plastic insulated wire, and the beginning of it at the bottom is grounded. And you'll notice that there's corona streamers coming off the top of this 8-inch diameter copper ball up here, shooting straight up in this region here, which is indicative of the fact that there's enough current flow in the ground connection on the base of the active coil here, which is grounded to a water pipe about 10 feet away. And the input of this coil is also attached to that same ground point. The distance between these two coils is approximately 7, maybe 7.5 feet. So you would not expect electromagnetic flux line coupling between these two secondaries, but rather sympathetic resonance due to current flow in the ground connection. And notice the purple sheet ionization is just almost a uniform purple glow in these regions here and here. That's a very unusual thing to see in many Tesla coils, where you get that kind of a uniform sheet ionization. And very much similar to what Tesla showed in his famous pictures from Colorado Springs, you have some of the discharges striking the side of the coil, as well as the majority of the discharge dancing about the curvature of the copper ball here. Again, there's just the single corona point there and the faint corona glow here. So what we've done here so far is we've maximized, with minimum effort, the efficiency of this active coil system, and we're causing enough of a flow of electricity in the ground connection that we can sympathetically resonate a coil such as this, which happens to be approximately 1 harmonic. And I say approximately, I have to emphasize that. It's not exactly against the resonant frequency of this coil, approximately 1 harmonic above. And at this point, I'd like to say that when it comes to magnifier coil construction, it has been my experience that the relationship of the resonant frequency, the self-resonant frequency of the extra coil, as compared to the primary-secondary system, whereas it is very important, it is not absolutely essential to be directly on. And oftentimes it's actually more advantageous if it's not. This gentleman here is a friend of mine named Jim Schaefer, who, because of his interest in Tesla coils, is someone that I met in 1975 and has become a very good friend of mine. And that's another interesting thing that I could expound on, which is when you are interested in something as Tesla coils, you meet very interesting people. This is, again, a standard 2-coil system, secondary, primary, and it's a helical primary in this case. Close-up view of that, it's 3/8-inch copper tubing, the diameter of the primary approximately 24 inches. It's on a 30-inch plexiglass base. There's RFI filters down below and a quench gap and a capacitor bank. The secondary 10-inch diameter cardboard tube, sonotube, commonly available, although these days I mostly use PVC, polyvinyl chloride, specifically the gray Schedule 40 that is commonly available. And that's approximately a 40-inch tall secondary. Notice the corona glow again between the primary and the secondary. And in the regions of the supports, which are made out of nylon, there are hot spots where, because of that dielectric surface, the partial discharges that are attempting to take place between the primary and the secondary, especially in this area here, follow that dielectric much more readily than they will follow open air space. That's another interesting thing about coil construction. Anytime you introduce a dielectric, you actually introduce a partial discharge leakage path if the dielectric is already severely stressed. This is a 30-inch toroid on top of this coil, and these discharges are coming right off the surface of the curvature of that. The input power is approximately 4 kilowatts. There's a metal plate that's placed over the top of the synchronous rotary gap, in this case, that was grounded, as well as a ground point up here. That arc path as a straight line distance was approximately 8.5 feet. And again, the winding height of the secondary from here to here, only 44 inches. Another shot of the same. Only in this case, I've again used that same technique of placing a small perturbation about the curvature of radius of the toroid. And so now you see all of this discharge issuing only from that one point. So it's an element of control, and also notice that the intensity of these power arcs is quite a bit greater than in that previous picture here, and certainly more numerous. Again, the corona glow between the primary and the secondary, almost a uniform sheet glow in this region. Well, of course, when you build big Tesla coils, you need big power sources, and I always show this slide. If you can't get what you need from jumping before your residential power meter, you have to find a more suitable power source. Such as this transformer here, and here's my friend Jim again, a 50 kilowatt transformer. Very well suited for high power coil construction with one limitation, what is normally referred to as the primary winding, because these pole pigs, as they are known, are typically used in step-down configuration for residential or industrial service. The high voltage winding, in any case, in this instance, is only 12 kV. Darn shame, isn't it? Because with a high power coil system, you typically would like to run a higher charging voltage than 12 kV. But it's such a beautiful transformer, I couldn't resist putting in a picture of it. This is a picture of yours truly with what I called a Model 10 coil. Again, a helical primary and secondary, 2-foot diameter, 9 feet tall, 10 gauge wire, approximately 2.5, 3 turns per inch. So it's a spaced winding. The orange color is due to the insulation that was placed on there, which is called Glipdol, or Glipt transformer type insulation. This was at an early stage of development, and as you can see, I looked quite a bit younger then, even though I'm out of focus. The primary here is only approximately 25 inches off the ground. And you'll notice that the coil form for the primary on these 1-inch nylon dowels gives rise to the thought that maybe this primary could be adjusted in height up and down, and that would be a true assumption. I did that on the basis of feeling the need to adjust coefficient of coupling. So I thought, well, I'll raise the effective center of the primary with respect to the start of the secondary and see where I get to the best results, rather than trying to change dimensions. That coil worked quite well. This is the same coil in a later stage of development. You'll notice now that these insulators have been placed underneath the base, and they're approximately 4 feet tall above ground. This is my backyard in Monrovia, California, circa about 1982, also known as RF Gulch, and there's a story behind that. This is a single pulse of the coil. That is just a quick tapping on and off of the power switch, so it's why you only see a couple of individual streamers. The toroid in this case is 4 feet in diameter, 1 foot in cross-section. These streamers going out approximately 15, 18 feet in random directions. The people over here standing underneath the garage door were rapidly trying to move back into the interior of the garage as this particular shot was being taken. Here's a close-up of that coil construction. And the interconnecting cable in this case is 250 MCM, or 250,000 circular mil welding wire. And the rubber insulation on this wire would get so hot after running this coil at power levels of 15 to 18 kilowatts, which was about the most that I could pull on my residential service before making my whole neighborhood go into a brownout condition, that you would smell the rubber insulation. The reason for taking this primary, this whole base area, and getting it that high up off the ground as compared to the first picture that you saw is to decouple the electromagnetic lines of flux of the primary away from what we call a ground plane, or just the concrete or the asphalt or whatever you have. That's very significant and important, because in a quarter lambda system or a quarter wavelength system, your first turn of the secondary is naturally going to be what? Ground. And in fact, you can see the ground feed-through terminal right here in this region. So if we are very close to ground level, we're losing some of our electromagnetic lines of flux set up in the primary by being absorbed into the ground. So one of the elements you want to strive for is getting a sufficient enough distance, decoupling the primary away from the ground, trying to put more of those lines of flux into the secondary so that when they collapse, you'll get a more efficient power transfer. Also seen in this picture, you'll notice this particular copper bar here that I'm pointing to and this insulator right here. That's 2 semicircles of 3/4 inch copper tubing. Each side is grounded at a ground terminal down below, but it does not make a shorted or one continuous turn. This is a safety ring, a corona safety ring, because the discharges from the secondary, when this coil was operated at 20 kilowatts or so in power level, were oftentimes so powerful that the discharges would come down and strike the primary, which is, again, a very serious no-no. That's how you lose transformers and capacitors, and it's also how it's possible to burn out light bulbs on the other side of your house or electrical appliances, because you get all kinds of back EMF into your power system. This is an early shot of the same coil with a 30-inch toroid on top, and you'll notice that it did not move the E field out effectively far enough away to provide what we call Faraday effect or Faraday shielding. And so we had a breakout of about a 12-foot long corona streamer here that burned the top 2 turns right off the coil, even though that was a single pulse. This is an elevated view of my backyard, and this was a transmission line experiment with a flexible aluminum hose going over and then down, positioned over the swimming pool, which is this area here. And this is that same coil as seen in a previous photo that was used with the Arant coil as a sympathetic resonant coil. It was just placed over out of the way. That's a 12-inch copper ball. The gap is about 15 feet. Here again is the 30-inch toroid with the 48-inch toroid on top of it with a small corona point. Now we have streamers coming out 25 feet in length with an input power of only 15 kilowatts. And this is the discharge on that transmission line experiment. The photographer in this case was a little nervous because these discharges were very powerful. And you can see here some of the characteristic signature of the antics of radio frequency high voltage electricity. That is, depending on various points along the transmission line, there'll be hot spots and dark or cold spots, if you will, in terms of corona activity. And anytime you have a short curvature of radius bend, a lot of corona activity because of no Faraday shielding. And then, of course, the main power arcs going down into the surface of the pool, as seen here. The total terminal capacitance of that transmission line plus the secondary coil amounted to about the same effective capacitance as a toroid almost twice the size of what I was using by itself, maybe almost an 8-foot toroid. These discharges were incredibly intense, blindingly bright, deafening to listen to, and you can see the attachment points right here and here where they're hitting the surface of the water. From this point looking down, this way you're seeing the reflection from the surface of the pool, and just like in natural lightning, the discharge actually splays out. It disperses and sends out little tendrils or fingers as it dissipates on the surface. Another shot of the same. This represents approximately a 3-second time exposure at just under 20 kilowatts input. Again, another characteristic signature, notice the combining and separating of these individual streamer channels. In this case, on the night that these pictures were taken, the air was very still, so we could not say that it was due to wind movement blowing the discharge. Rather, it was a matter of, I'm not exactly certain what it's a matter of. It's the same sort of thing that natural lightning does, even though there may not be any wind, the various striations of the discharge. Let's talk a little bit about spark gaps, because to me there's nothing more important for a spark gap driven Tesla coil than the design of the spark gap circuit. And for any of you who look at classical electrostatics in the physics books, you'll see illustrations similar to this. A ball gap and a representation of the electrostatic lines of force, fairly uniform in this immediate region between the two opposing electrodes, and becoming very distorted and nonlinear as you go out further from that point. Notice, as compared to a point gap, the concentration of those lines. This would represent ionization between these two electrodes at a much lower voltage as compared to the ball electrodes. Two parallel plates, and in the area between the plates, a very uniform field of electrostatic force, and perturbation of that field reaching out on the edge, and of course it would go further out as you would draw those lines out because of a phenomenon known as edge diffraction, the same thing that you have in antenna theory. In the mechanics and physics of a spark passing between two electrodes, let's say of parallel-faced material, what is occurring from nanosecond to nanosecond, microsecond to microsecond? There is, of course, a random distribution of electrons in the atmosphere, and as we all know, the process of a spark occurring means the linking up of electrons passing from one face to the other. So in moments just before, and I say moments as in very infinitesimally short periods of time, if one were to be able to study that in slow motion, you would see that there are actually clusters of electrons that group together of like signs, and that these clusters then link together. There are many elements that make a spark gap nonlinear. This represents what occurs immediately after the start of a passing of a charge from one point to another, some starting of linking. It's an oversimplification, but I believe this to be true of any spark gap design. Of course, even if these two electrodes in our model are grounded, there would actually be an accumulation and a uniform distribution of free electrons about the surface, more so than in the airspace in between. The difference here, and this is very significant for any Tesla coil, a cold electrode, that is temperature-wise cold, will have fewer free electrons emitted from its surface than a very hot one. And the classical experiment that proves this is to take an induction coil and see how big of a spark you can get with it, maybe a ½ inch, between a needle gap even, and then introduce something like a candle flame and watch that arc pass a distance almost 3 times that width, maybe 1.5 inches. So in terms of Tesla coil construction, that is a no-no. You don't want that kind of easy and protracted ionization. Geometry of gap material. In terms of material that's very narrow in cross-section or very short, one would necessarily have to run a fairly large distance between those two electrodes as compared to this much shorter distance of a broader faced surface. The geometry of that material is also important. In terms of rotary gaps, whether you run synchronous or non-synchronous, the important thing to consider is what is the terminal velocity of the rotary electrodes, so that you could calculate what is the mechanical dwell time of what I call candidate target area, where the rotary electrode comes within striking distance, electrical striking distance, of the stationary electrode. And you'll see also in the design of rotary gaps in wireless technique from the 20s and the 30s that many people were aware of these things. Another thing, if we were to look at the surface of any gap material, I don't care what it is, could be tungsten, could be copper, brass, cobalt, steel, anything. If you looked at it in terms of microphotography or electron scanning photography, you would see a very serrated surface, very nonlinear. This translates into these areas as being the peaks, the areas where the first electrons would pass. One would want to have a very uniform surface, because what is important with a spark gap? It is a commutator. Tesla always referred to it as a commutator, an on-off switch. We want it to be infinitely open or high impedance during the charging portion of an individual oscillatory cycle of the Tesla coil. And then we want it to go to virtually no impedance, like a direct short, so that we can dump as much of the energy from the oscillatory capacitor into our primary inductance as possible. Different types of gaps. These are faced with thoriated tungsten. They have copper heat sinks in the form of hex nuts and a cast aluminum block. This represents a 6-inch machinist's rule for scale. This is a gap that was taken from a standard tungsten inert gas welder, TIG welder, that many of you would be familiar with. You can actually find these sometimes in large industrial welding supplies. They work very well for Tesla coils of moderately low power. Ball gaps such as here and here, with the same small gap here by comparison for size, are good mainly for safety gaps, as an over voltage crowbar, if you will, brute force crowbar, for protecting your transformers and for your capacitors. They do not work very effectively for even moderate-sized Tesla coils. You can certainly do better than that. This picture is taken from Elmer Butcher's book called Wireless Telegraphy, circa 1920. And in those days, they were aware about the heat problem, about keeping the electrodes cool. They were aware also about having parallel surfaces of large surface area and a fairly narrow gap distance. This gap would actually work fairly well up to about 1 kilowatt of power input. And in this case, they used zinc, which is a material that wears better in terms of degradation of the surface of oscillatory discharge as compared to standard steel. Look at the variations in design, again taken from Butcher's book. Up here is a non-synchronous rotary, a single stationary electrode, multiple rotary electrodes, a commutator ring here, assumably motor-driven, and a fairly narrow gap distance, that is, in terms of cross-section. So one might think that that would work very well for a Tesla coil, and you'd be right. The gap here with this concave stationary electrode would imply a very long dwell duration, which means that you'd have to run that with a very, very, very loosely coupled Tesla coil, because, of course, when you have a tighter coupling, you have to shorten up the dwell time. This design here is referred to as a Marconi disc discharger. Notice that it has stationary electrodes and a insulating disc with rotary electrodes sticking through on either side, the motor shaft being about the center of that disc. It turns out that this is yet another example of Marconi's borrowing, quote unquote, Tesla's technology and Tesla's designs. This represents a very large parallel gap that is a stationary gap. Here again, we have a gap of large displacement with a curvature of radius, but only to the extent that it is a hemisphere of the diameter of these, with an air blast to extinguish the low-frequency arc. In other words, increase the quenching or increase the damping of the gap. Down here, a cross-sectional view and an illustration of a quenched gap, which was a hybrid that was developed after non-synchronous and synchronous rotaries. The tick marks here on the sine wave represent enough of an EMF rise on this half sine wave down to the zero crossing point, and again here on the negative side, where you typically could have a spark gap fire. But you don't necessarily want to do that. If you run a synchronous rotary, you can group those together depending on your input power, and assuming 60 cycles or 60 hertz, you could time that so that it would fire only at the peaks or on the skirts just below the peaks on either side, which turns out to be just about optimum, because that way your transformer does not see that spark gap looking as much as a direct short as compared to if it fires right on the peaks. And as you put in more and more current on each half sine wave, of course, you'll have more individual oscillatory pulsed wave trains, because you'll be putting in more power per unit of time as compared to if that was not the case. Again, from Tesla's book, you'll recognize this illustration. Again, all the methodologies used to create a gap that quenches very well, allows the oscillatory spark to pass, but not a low-frequency arc to form and ruin the damping. So these balls were able to be rotated about these cup holders, and there was a thin sheet of mica introduced as insulation and two strong opposing poles of an electromagnet. A number of Tesla's illustrations are significant. If you study them, Tesla teaches us all a great deal about gap design. And yet, one of the strange things about Tesla's teachings on spark gap design is that when it comes to the Colorado Springs and Wardenclyffe coils, he tells us very little about gap design. This example here was an alcohol burner to introduce a gas to help quench the discharge. Multiple segmented stationary gap again with an air blast. These are all from Tesla's book. Again from Butcher's book, a concentric synchronous, actually I should not say synchronous, a concentric rotating quenched gap. This one was called a Benwood gap, fully enclosed in a metal case, 2 insulated bushings and an insulated rotating disc discharger inside. B.F. Campbell rotary gap circa 1915, and a Murdoch gap circa also 1915. Non-synchronous, good for amateur work, amateur wireless. That's where these were mostly used. This is an example of rotary gap that I built for one of my higher power coils. The stationary electrodes are of solid thoriated tungsten. The rotary electrodes are faced with tungsten buttons a 1/2 inch in diameter. There's actually a double gap, one here, and the same on the opposite side, so it actually is a double rotary. The motor is converted from 3450 RPM to 3600 RPM so that it will be dominant pole or salient pole synchronous. That's done by fly cutting the armature. In the case of a 3450 RPM motor, you have 2 field windings. The squirrel cage shunt armature, therefore, must have 2 opposing flats on it of appreciable area to create 2 dominant poles that will follow the rotating lines of magnetic flux set up in the field winding. Another view of that gap, and if you look closely here, you'll see all of this discoloration, or not pitting, but actually a coating. This is the trailing edge of this gap. That is, the direction of the rotating member is from left to right. And this is the trailing edge of that. And that is actually almost a sulfur type powder that you get from running tungsten electrodes and getting them very, very hot. And in fact, this gap was run so high in current that these tungsten buttons would heat up, even though that this is a base metal essentially of brass, and this is 1/2 inch brass rod stock here, and you have a lot of cooling because of the 3600 RPM. Still the same, these tungsten surfaces would get so hot that it would just melt them right off their spot welds on the surface. This is an example of a stationary electrode with cooling fins that occurred to right there. And I think we just lost our slide projector. No, we didn't. That's the end of the slides. Okay. Anyway, so all I'm trying to do is say that spark gap design is the most important element, other than good coil design itself, for a magnifier or anything else. All right, brief description of what we have here. It's what I call a Model 5 magnifier. In the front, we have a total of 4 capacitors. They're 0.02 microfarad polypropylene, 20 kV capacitors. These were made by Hypotronics. We have a total of 5 turns possible on the primary coil of 1.5 inch width copper tubing. They're spaced approximately 1 inch per turn. The secondary is 16 gauge PVC insulated wire. It's stranded wire. It's tight wound on this PVC form that's 10 inches in diameter and approximately 16 inches tall. I've placed insulating discs inside here, and the beginning of the winding as well as the last turn are constructed so that they pass on the outside surfaces of those 2 lucite discs that are silicone sealed to the inside to prevent the possibility of arcing down the center. Another interesting thing that I've come up with in my experiments over the years is that you achieve 3 basic plateaus of operation with the Tesla coil. First of all, you're going to get the maximum EMF rise that you can get. Secondly, past that point, as you do better tuning and more input power, you'll get the maximum amount of available current that you're going to get at that voltage level. The third thing that happens is that you melt down the winding or you burn up your coil form past that point, because everything else goes up in heat loss, and it's at the point where the coil is giving you as much power, usable power, voltage and current as you're going to get, that you run the risk of getting that premature breakdown down the center of the tube. There's 2 elements that prevent that from happening at lower plateaus of operation, one of which is that the electromagnetic lines of force coming through the center of this helix or inductance help to inhibit the possibility of ionization. But we've all experienced, I think, carbon tracking down the inside surface as a leakage path. Okay, we have a 20-inch toroid here. Here's our transmission line, quote unquote, just an electrical conductor. Here again, borrowing from some experiments with electrostatics, in order to eliminate corona, I don't want any leakage here. That's the reason for the small 14-inch diameter toroid. The insulator is strictly vaudeville, if you will, or theatrics. It's an insulator that I had, and I decided, well, that makes a suitable stand for, or pedestal for this extra coil. Tesla, in one of his patent applications, describes a very tightly coupled primary and secondary. It's one of the most significant patents of his, describing a system for wireless power transmission using a magnifier, wherein the extra coil is very narrow in diameter and very tall. So it has a very unusual form factor. And I've decided that, well, I'd like to experiment with that too. This is the first magnifier that I built that was actually a separated system. I've built magnifiers before where the extra coil stood directly on top of the secondary, and in fact that was shown here in Colorado Springs across the street at the Red Lion Inn. No, scratch that. Make that the Hilton in 1990, because Red Lion was 1988. In any case, this is a phenolic form. This is 20-gauge wire, hyperpolythermalese, or form VAR, as it used to be known in the old days. Enamel wire. It's solid wire. It's close space wound. It's covered with varathane plastic coating. And notice up here on top, huge by comparison to the rest of this, terminal capacitance of a highly polished 30-inch toroid. Now in this system, that turned out to be very important, because as I was trying to maximize the efficiency of this, that is maximum bang for the buck or maximum spark for the buck, what I learned was that just having like a number 32 sanded finish, it would easily issue out discharges in all kinds of different directions. I got it to the point where, as a highly polished surface, it would build up to a much higher voltage and higher current, therefore, before free coronas would break off of that surface. Another thing that I found of great interest was what occurred when I changed the coupling coefficient between the primary and secondary by raising or lowering this coil, the secondary coil, in and out of the field of this primary without changing any other parameters. So I have these little green insulators here. There are two of them between this blue base and the bottom of this coil. So that means that the first turn of the secondary is approximately level with the very top edge of the primary. Removing one insulator would drop that down to the bottom edge. And as exhibited here last summer at the Extraordinary Science Conference with just one insulator, it was very easy for me to put in more and more power to the point where it would break out in big long discharges coming off of this polished smooth surface. But going up 2 insulators or even 3 insulators, I had no breakdown. I could put in the power all I wanted, but nothing would come out here. It would just sit there and you'd hear the rotary gap and you'd see corona streamers along the transmission line, but nothing coming out. Then I could take a penny, just something like a penny, and just lay it up here. Not very much of a perturbation, and that would serve, and as Richard and I found out again last night at Penrose with the big system, that when you have a perturbation that's just of the right size, that'll help issue the discharge. I know that you can all hear me fairly well, and I'm going to remove the wireless microphone now because we'll go quickly into the hardware demonstration of this, because after all, that's the significant part of having this here, is to demonstrate different parameters. So with that, I'll take the microphone off and also turn it off at the same time. Up here on stage, the power supply source is a 1.5 kVA potential transformer that we use in substations. These are designed mainly for indoor service. It's a 150 to 1 ratio, capable of 1.5 about making it variable, again here specifically working with magnifiers, at least on this level, is characterizing the different nature of the discharge depending on the repetition rate. Remember that the oscillatory pulse is a function of the L and C values. Directions of discharge push out. Remember that I talked about the coefficient of coupling affecting the performance of the output of the extra coil. Now, if I operated this thing here, and my reference point on the variac dial here was 130. So I have a way of seeing what my input power was. So I'm going to turn this down to 0, and now we have nothing but the smooth curvature radius on there. And I'll bring it up and we'll see if we get any pretty bonus emanating off that surface. can pull out of my bag of tricks here real quick. Ah, here we go. This is ideal. I have here a small Phillips bit. Phillips power driver bit. I'm sure that will be sufficient to cause the irrigation on the lower. That is, it stays there. do this. This is worth a lot of money, and that's kind of a difficult thing to balance on there, but that's what I'd really like to be able to do, if at all possible. Now, the question is this. Yeah, you can stand right there. You can't do this call here. Oh, right, yeah. Okay. Well, I guess that's why we have symposiums, right? That's where you put everything on the line, right? So, a lot of corona on the transmission line. Let's put up a little corona point. See what we get. Sure not getting enough to drive that thing very hard. Ladies and gentlemen, all I'm trying to do here is to graphically illustrate how radical can change certain parameters and how it'll really change the results obtained quite significantly. Okay. Well, we're in the right direction. So now suppose, now if I could have you to just put your hands there to hold it, because what I'm going to do is I'm going to change the capacity here. All four of these capacitors are in parallel, and I have the ability to remove one or two or more at a time. So I'm going to take one capacitor out of the circuit and go from 0.08 microfarad down to 0.06. Let's see if that buys us anything in terms of performance. Okay, thank you. Going in the right direction. Okay, let's take out one more capacitor. Go down from 0.06 down to 0.04. Okay, only one capacitor in the circuit. 0.02. Okay. Right? All right, and quickly, let's go back to our original configuration just to reconfirm that we were close at the 0.04, but I couldn't compensate enough with capacity. I would have had to also adjust primary inductance. I was in the ballpark, but not right there. So we'll take this off. We'll take that coil off and set it aside. And put this back on. Maybe I can get you to do that for me. Meanwhile, I'll put the capacitors back in the circuit. Let's go back and reconfirm the original hookup here real quick. And that will be the end. Except for questions that I can answer quickly, because I don't want to go into Richard's time with his paper. Yeah. And you'll have to rotate it around so the level is one place which is properly level. Here's a test of coil experimenting heat step. Okay. Put all four capacitors back in parallel, so we're back to 0.08 microfarad. Of course, you can easily understand that there's, we have the steel top. Okay. Oh, incidentally, this gentleman who is assisting me right here deserves special attention as does his Mrs. Tony Chalemi, KB6IFC. Without his help, the big magnifier without a Fendos would nowhere near be finished in time for this conference. How many tie wraps did you put in the cabinet? 2,000. 2,000. Wow. And he's got carpal tunnel syndrome from his tie wrap gentleman. Now let's see. We have that little point that's only just under a quarter-inch cross section. We'll kind of stick that back up here again. Just lay it sideways there, right along the top. And we'll see if we're back to our normal operation here. Let the gap build up. I've left it at the slower speed because it's approximately synchronous. That's where we seem to get our longest discharges. So that meant we were doing the best power processing that we could do. I get nervous as things start vibrating. After last night, certain people in the audience know why I say that. Okay, here we go. Okay, ladies and gentlemen, thank you for your attention. I'll be happy to answer any questions quickly. And I know Richard's
Okay, we're going to just jump into our first session as fast as possible. If a couple people can start getting the chairs reassembled, and Richard Hull come on up, and we'll be on track pretty quickly here. Boy, that sure beats a couple of cups of coffee for waking up, doesn't it?